Okay, so I'm a PhD student under Professor Tina Ng at UC San Diego, and I'll be expanding on my abstract to talk about structural supercapacitors with high multifunctional efficiency. So supercapacitors are electrochemical energy storage devices that are known for having fast charge discharge times and a long cycle lifetime. So batteries can typically cycle at least 500 cycles before they start degrading, but supercapacitors can go for at least 10,000 cycles before they start to degrade. And because of their fast discharge time, they're known for having a high power density. So as you can see, compared to batteries, supercapacitors can be 1 to 2 magnitudes higher. But in comparison, they hold less capacity overall. So they're known for having a lower energy density, which is also about 1 to 2 magnitudes lower. So these are useful for our network devices, flexible electronics, transportation, or any applications that need a quick high burst of power. But to make it more easily realizable, we need to have a higher energy density. So the way we decided to do this is by using structural supercapacitors. So structural supercapacitors are integrating the load bearing and the energy storage components. So we increase the active material area by putting it in the hull of the device. And then we can also reduce the weight. So when we look at like cars and boats, they already use carbon composites for the same reason that we use it for our energy research. They're lightweight and they're very strong. So it's very easy to integrate these two together. There's a few extra considerations when it comes to structural supercapacitors, because it's easy to end up reducing both the power and energy density instead. So when it comes to the electrodes, already for monofunctional supercapacitors, there's a concern with active material delamination and degradation over time. And then we need to put it on a substrate that is stronger, such as carbon fiber. So any chemical activation processes for the active material can end up damaging these fibers. And then the active material itself won't contribute to reinforcing, so it can fall apart very easily. And then the next consideration is our solid state electrolyte. So going from a monofunctional liquid electrolyte, we need to have a structural strength. So it needs to be more rigid, but then the rigid electrolyte can end up blocking the charge exchange sites. And from that point, if we try to improve the ionic conductivity, it can greatly reduce the mechanical strength. So the key to make this work is to have a good electrode-electrolyte interface. And I'll be talking about first our structural electrodes, electrolyte, and then our full device. So before we move to the structural component of the electrodes, there's two ways to increase the energy density, and that's increasing the capacitance or the potential window. So prior works have used organic polymers and metal oxides, and these have a high capacitance but a lower voltage window, which reduces the overall energy output. And they also have a low cycle lifetime. Our group has worked with the N-type QXTH polymer in the past. This has open shell redox states, and it has a lower capacitance overall, but it has a high potential window because we can extend into the negative range here. So we have a good polymer to use, but we can still improve the capacitance. So typically to deposit a polymer like this, we need solubilizing groups to make a solution and then coat the carbon fiber substrates. But once it's coated, these additional groups don't contribute anything to the redox capabilities. And they just add extra weight and make thicker electrodes that reduce the power density, which is the key advantage of supercapacitors. So instead we came up with electropolymerization, which is we broadcast the monomer QXTH slurry directly onto the carbon fiber substrate. And then we apply a constant current to synthesize the polymer directly from the monomer. And then once the voltage stabilizes, the reaction is complete. So you can see here's pure carbon fiber strands. And then this is our coating after adding QXTH. And it also includes reduced graphene oxide in the solution. This has no capacitive capabilities, but it helps stick more QXTH on to create a more porous coating. And with that, we can have thinner electrodes with high kinetics. And then looking at the electrochemical performance, we cycled it in the cathodic and anodic region over our 3-volt window, and with a high loading of 3 milligrams, and we achieved a cathode-specific capacitance of 34 farads per gram, and then the anode 64 farads per gram. And it was able to cycle at least 10,000 cycles and retain about 96% of its capacity. So the electropolymerization worked to adhere the electrodes firmly. Next, looking at the structural properties, here's the pure carbon fiber and then our QXTH electrodes. They have a similar maximum tensile strength, but the tensile modulus increased to 103 gigapascals, and this is because the slurry was able to bind the fibers together and reinforce it. So if we compare it to other state-of-the-art structural electrodes, our tensile strength is about 1 magnitude higher, and our capacitance is still 1 magnitude lower, but it's important to note that these works did activation processes on the carbon fibers that ended up reducing the stability overall. Okay, now it's time for the electrolyte. So a typical solid-state electrolyte uses epoxy to bind the separator and the electrodes together. And so that gives it the mechanical strength. And then a conducting salt, we're using TEAB of 4. So prior works have used this combination, and it ends up blocking the redox sites. So we also added the ion-conducting polymer, PEO. So PEO adds percolation networks and helps boost access to the electrolyte salts. And then we played with different variations of this formula and found that if you have a higher salt ratio, you'll have a high conductivity but lower strength. And then if you increase the PEO a lot, it still reduces the strength overall because it's not as viscous as the epoxy. So we came up with the gradient electrolyte. Our gradient electrolyte uses regions 2 and 3. So region 3 is near the electrodes. It has our high salt ratio and the medium PEO ratio. So the higher electrolyte salts here help boost the redox performance and keeps the channels active. And then the middle region has a higher epoxy ratio to reinforce the device and any external load that would be placed on it. And then you can see here is the electrolyte filling in around the carbon fibers. Next, we can look at the electrochemical and mechanical properties. So this green line is our uniform PEO epoxy solution. So this has the highest flexural strength of 130 megapascals, but a low ionic conductivity. And the blue line is our high salt ratio, which has the lowest flexural strength, but high conductivity of 0.4 millisiemens per centimeter. And our gradient electrolyte keeps the same conductivity and then reaches a higher flexural strength of 91 megapascals. And then here is our PEO liquid electrolyte in the orange line. So we won't achieve this performance because we have a need for mechanical strength. But you can see that our uniform PEO epoxy solid-state electrolyte, the green line, it has slower kinetics, which is shown by the loss of the redox peaks, but our gradient electrolyte is able to bring it back. And if we compare our electrolyte to other solid-state electrolytes used in monofunctional supercapacitors, it can outperform these as well. So if it's good enough for those, it's good enough for our structural device. So finally, here's the full cell laminated together. Here's our gradient electrolyte able to hold up 100 grams, and it still has that high conductivity of 0.4 millisiemens per centimeter. And then here's our 3-point bend test. So its maximum deflection is 7 millimeters, and it retains 85% of its capacity. And you can see point by point, it's consistent until 3 millimeters, and then it starts decreasing to 85, and then it breaks after 7 millimeters. And it's able to cycle for at least 10,000 cycles and retain 84% of its capacity. So now we have a final working full cell. Another thing we did to improve the efficiency is to make multi-layered devices. So most of the device weight is made up of these carbon fiber substrates. So besides the active area, it's just additional weight. So what we did is we coated both sides of the substrates to make double-sided electrodes and then stacked them together and made our full cell. So this 9-layer device would be worth 8 2-layer devices, but it uses less carbon fibers and electrolyte overall. And it reduces the mass by 57% compared to the individual devices. So because we're able to increase the loading per unit area, we have a higher current output and a higher capacity. And we improved the energy density by 1.57 compared to those individually stacked devices. And then because it's structural, it retains the same flexural strength as our 2-layer device. And then finally, we can look at our performance against prior works by looking at our Ragone plot and multifunctional efficiency. So here's the power and energy comparisons, and this blue area is structural supercapacitors. The gray is monofunctional supercapacitors, and the yellow is structural batteries. So for our 2-layer, 9-layer, and a 9-layer device with the higher active material loading, they all outperform prior structural supercapacitors, and these middle regions reach monofunctional supercapacitors. And then for the 9-layer devices, they're actually able to reach the structural batteries, outperforming this iron oxide battery. And then next is the multifunctional efficiency. So this looks at how good it is compared to using two separate monofunctional components. So we have a baseline electrical and mechanical value. And if these together add up to more than one, then the weight saving is worth using this device over the two separate components. So as you can see, fireworks don't meet it except for this one, and they all skew to high mechanical strength, but no electrochemical performance. But our 2-layer device is able to meet this threshold with our 9-layer devices exceeding it. And finally, we have our proof of concept. This is a model boat where the hull is made of the structural supercapacitor I showed you. And it uses a solar cell to charge it up, and then it rapidly discharges and propels the motor forward. So that high power density by the structural supercapacitor is what helps this boat, and it's something that structural batteries cannot do. That's all. So yeah, today I showed you our high energy density structural electrodes through electropolymerization, our gradient electrolyte design that has high mechanical strength and conductivity, and then our proof of concept structural boat. And as you can see here, this is a commercial carbon fiber boat being sold, and its whole inside looks exactly like what I showed you. Yeah, and finally, thank you to all of my lab members, our collaborators, and our funding from NSF.